Greetings to all. This is Prof. Raja Subramanian here to mathematically explain convolutional neural networks. In this video, you will clearly understand the basics of convolution mathematically, and you will be in a position to solve any problem with respect to convolutional neural networks. Basically, in the previous videos of all-in-one, we have discussed like how to practically implement a CNN and various ImageNet models. But in order to cater the basic requirements of understanding CNN mathematically, like we have several layers in CNN, say convolutional layer, pooling layer, padding layer, then we go with dense layer, dropout layer, and final output. Now, this convolutional neural network involves the basic convolution, padding, and pooling. So it is necessary to understand how an image get convoluted and what necessarily is the use of convolution. For that, let us go into the basic problem and understand it in detail. So this is what the example I have taken. So convolutional operation by default, we actually say convolution as a compression. So we say it is just a compression kind of thing, and assume that we have an image and that image need to be compressed. This compression can be like when we actually require an image which is actually having only the required features or features that is most important in that image, then we do compression. Or if you have a very big image and we need to reduce the height and width of the image, then we do compression. And that compression we call in deep learning way as convolution. So assume that I'm having a matrix representing an image. Usually any image is represented as a matrix of its pixels. Pixels is nothing but a single unit of an image. So various pixels will group together and form an image. So each image, I call it to be a two-dimensional matrix. So assume that I'm having a 6 cross 6 image. Say for example, we have a 224 or 200 cross 300 image. Means that you have a 200 width image and a 300 height image, a good portrait image. Likewise, let us assume a square image of a very small size, say 6 cross 6, which is having totally 36 pixels. So the image size is actually 36 pixels. So I'm having some values inside the image. So that values is nothing but the pixel value, which represent the particular color. And this pixel value can be either 0 or to the maximum it can be 255. Why? Because there are actually totally 256 colors. So starting from 0, it will be from 0 to 255. So that many number of different pixels are available in different color notations like R, G, and B, red, blue, and green. So which can group together to form a beautiful image. So when we go for convolution is I don't want 36 pixels and give me only a small number of pixels which is necessary to take only the important features or important pixels in the image. So that is why I will go for a convolution. So when I go for convolution, two things I require initially. One is called as filter and the other is called as stride. This filter is nothing but kernel. The kernel is nothing but the main part which is used to take convolution. Say for example, we have a rice flour which is being given to a filter which takes only the powder alone in the droplet and takes all the stones on the up. So such a filter is actually used here. Like I'm having a 6 cross 6 image and uses very small filter which it takes only the important pixels related to that particular filter alone, so that the image size will get reduced to only the important featured image. This stride depicts like how much small image you want. The rate of compression can be represented as stride. So let us see mathematically in addition to theory. Assume that I'm having a 3 cross 3 filter. So this is again a matrix and the stride value is by default is 1. So let's proceed to convolution operation. So initially I have a filtered image, say the initial thing 6 cross 6, which is the input image. Then I'm having the filter size this. So 3 cross 3. So when I do convolution, take the size of the filter and put it inside the image. So I put it inside the image to get the image representation. And if you see the red box which I have been putting here in the original image is equal to the size of the filter. So my filter size is 3 cross 3. So inside the convolution original image as well, I put a 3 cross 3 box, meaning that I have to multiply scalar wise each component in the image with the filter component. So 1 into 1 plus 2 into 1 plus 5 into 0 plus 1 into 2 plus 3 into 1 plus 6 into 0 plus 2 into 1 plus 5 into 0 plus 1 into 7. So this is what I have represented here, like the original image dimension pixels as blue color and the filter dimensions as in red. So that clearly says how it actually goes on. So this filter size now is actually the essential component, and based on this only, the image will get convoluted. Next, what you will go for is the stride. So when you take the input image as this, and if you want to proceed to the next image, then what you actually go for is to enter into the stride. So when I take the stride value for the next component, my stride value is 1. So means that I have to move this box one step ahead. So my next component will be 255368510. So the convolution operation will do 2 into 1, 5 into 1, 5 into 0 plus 3 into 2 plus 6 into 1 plus 8 into 0 plus 5 into 1 plus 1 into 0 plus 0 into 7. So this is the use of stride. So the next component will be this, and my next component will be this. After I'll go down further. So next my down will be this, one step further down. So this is how I go in the next step, and in the subsequent step this will be my subsequent step, and following that I'll be going with this is the next step and so on. So in this way the stride is actually used to denote the step size. If I make, say, if this is the original first dimension and the stride is equal to 1, then I will make this box to move one step. So if I make stride equal to 2, what happens, you see, this box which is in the original dimension will directly move 2 steps. So say if 1, 2, 5, 1, 3, 6, 2, 5, 1 is there, I will go 2 steps further, so directly it goes here. Because I am skipping 2 columns at once. Similarly, if I want to go down, I can go, if it was the original position, I'll go 2 rows down. So this is what my next position. So that is how stride value changes. So if you increase the stride value, the amount of steps I take in convolution also increases. So that is how it actually goes. Now, when I do convolution operation with stride equal to 1 and with this 3 cross 3 filter, this is my answer. So now if you see the original image is, which is 6 cross 6, 36 pixels is now compressed to 4 cross 4 dimension, which is 16 pixels. So before doing this operation, let us have any formula for this. Like if I give the filter size and stride size, will there be any formula for calculating what will be the output map given the input image size? So this is the formula, like the compressed image dimension will be equal to n, which is the original image dimension, f, the filter size, s, the stride value, plus 1 constant, plus 2 into p, that is the padding value. Here we haven't did any padding. Padding is nothing but just surround your image by zeros, so that if you want to do any pooling or any other striding value, if you didn't find the columns, pad it with empty zeros. So here I didn't find any of those concepts. Since it is somewhat advanced, let us see about padding in the subsequent video. But the general formula includes 2p. Here there is no padding, so I put p equal to 0. Now for the above example, let us assume that we have a 6 cross 6 image, so n is 6. and I have a 3 cross 3 filter. So F is 3 and stride is 1, which is the default one which I have taken. And as I explained, padding is equal to 0 for our example. Now C is equal to 6 minus 3, n minus f, 6 minus 3 divided by 1 plus 1. So which is equal to 4, and hence that is what my answer 4 cross 4, a compressed image. Yes. Immediately after convolution, we'll do something called as pooling. So what is that pooling? Is nothing but if you compress the image, the original dimension of the image will get decreased. So people seeing the compressed image should treat this image also as original image. So in order to look into the dimensional changes, there should be some mechanism to say that the original image and the compressed image are alike and they are not different. So to make it scale invariant, that is bigger image or smaller image or any sized image, they are same. In order to say that they are same, we need to do something called as pooling. And there are two types of pooling involved there, and those are called as max pooling and average pooling. Both are simple concepts. Let us assume that the output activation map, which we actually had in the previous example, we will take that map, and what I have to do is pooling usually decreases the original dimension divided by 2. Because if the original dimension is 4 cross 4, the pooled dimension will become 2 cross 2. That is, it will give 50% of the image. So that is the heaviest compression you call. So if I have the original dimension 4 cross 4, I keep it the windows, I keep 4 different windows here, each of dimension 2 cross 2, the 50% of the original. In this, if you see 17, 24, 25, 75, the max value is 75, so I put 75 in the max pooling result. Similarly, 38, 49, 38, 78, I go with 78 as the max value. 67, 30, 41, 63, I find 67 is maximum, so I put 67 for that particular window. Similarly, 16, 33, 59, 67, I find 67 is the max value, so I put 67. So I hope now you clearly understood for each window, I'm taking the maximum available pixel. So that is why it is called as max pooling. Then on the contrary, the average pooling is nothing but take the particular window, say 17, 24, 25, 75. The average of this particular window was 35.25. So it is average pooling, that is nothing but for each of the window, I have to take the average value of the available pixels. So, and that is why the differences. But why these two types of pooling and what is the necessity? Now, max pooling is used in context where the most dominating pixel alone should be taken into consideration rather than other pixels. Some pixels are less contributing or less dominating. So the most important pixel, which is the maximum value holder, alone will be taken into consideration during compression. So that is what max pooling says. The phenomenon of average pooling is slightly different. That says either the pixel is dominating or not, its contribution should be valued. So I take all the pixels in the particular window, take the average of that with equal weightage so that the contribution of all the pixels is taken into account when you do compression. That is what average pooling is. So this is all about convolution and pooling. And let us go with an example like how convolution and pooling will go in real-time representations. So assume that I'm having a 300 cross 300 image, a big image, assume again square. And for this 300 cross 300 image, I want to do a convolution 2D operation with filter size equal to 10 and the stride value equal to 2. Followed by I need to do a pooling operation. Then again I have to do a convolution 2D with filter 2 and stride 1. Again I want to do a pooling. Again I want to do a pooling. Then I want to do a convolution 2D with filter size equal to 2 and the stride equal to 2. Now if you see, I have 1, 2, 3, 4, 5, 6 different operations that need to be done in this convolutional neural network. So this is the neural network. I give an input image, first to do convolution, then pooling, convolution, pooling, pooling, convolution. So see the network, how it goes on. Now, practically, before you go, you have to mathematically understand how will be the activation map. That is the final resultant compressed image. For that, let me actually remember my formula. C is equal to n minus f by s plus 1 plus 2p. And again, here also I am not going with padding because the use of padding is not required here. So I take p value equal to 0. And I take the first process of operation, that is convolution 2D, with filter size 10 and stride equal to 2. I know the original given image size was 300. So 300 minus 10 by 2 plus 1 constant plus 2 into 0. Padding is 0. So 0, I get 146. Next, I have to do pooling. And we know that pooling will divide the image to 50%. So 146 by 2, 73. Then again you do convolution for this 73 pixels. So 73 with filter size 2, stride 1. So I have plus 1, I get 72, that's this time. Next, again do pooling. So it becomes half, 36. Again do pooling, it becomes half, 18. So the final operation as given in the question was again a convolution with filter size 2 and stride equal to 2. So this will give you 18 minus 2 by 2 plus 1, which is 16 by 2, 8 plus 1, 9. So the final dimension of your image after all these convolution operations is 9 cross 9. And that's simple how convolution neural network is. So this is how a real-time convolutional neural network works mathematically. I hope you have completely understood this convolutional neural networks. And for more examples like this, refer my video and subscribe it for more upcoming videos on padding, RNN, and elsewhere. Thank you.